Welcome to this explainer. If you're a UX, UI, or HCI professional, you already know the drill. Design isn't just about making things look pretty. It's about making hard decisions backed by rock-solid data. So today, we're demystifying the data journey. We're going to take what can honestly feel like an intimidating, sweat-inducing math class and turn it into a highly practical, absolutely essential toolkit you can use right away.
Here is our roadmap for today's explainer. First up, decoding your data. Number 2, testing the hypothesis. 3, choosing the right tool. 4, avoiding costly mistakes. And finally, number 5, measuring real impact.
Okay, let's dive into this. Have you ever launched a massive UI update, watched user engagement tick upward, and then quietly wondered to yourself, did my new design actually work, or was I just lucky? Well, that is the core tension in UX research. Every single time we test a new feature, we are literally trying to separate genuine human behavior from pure random chance.
Let's start with section 1, decoding your data. First up, the foundations of data.
To answer that big, was I just lucky question, we have to rely on random samples, right? Because you simply can't test every single person who will ever use your app. And the absolute magic that makes sampling work is the Central Limit Theorem. It essentially says that as your sample size grows, the distribution of your sample means approaches a normal, bell curve shape, totally regardless of what the underlying population looks like. The standard rule of thumb here? Once you hit a sample size of about 30 or more, you generally have enough data for this mathematical magic to kick in, letting you confidently estimate the true behavior of your entire user base.
Now, that mathematical foundation dictates how we actually record our data across 4 distinct levels of measurement: nominal, ordinal, interval, and ratio. It's like a giant puzzle. Nominal data just groups things, like asking users for their preferred cereal. Ordinal adds a logical hierarchy, like a Likert scale from strongly disagree to strongly agree. Interval data gives you equal spacing but no true zero, like temperature in Celsius. And finally, ratio data gives you both equal spacing and a true zero, like measuring a user's reaction time in milliseconds. Knowing exactly which bucket your data falls into is absolutely crucial because your data's level dictates exactly which mathematical operations and statistical tests you're actually allowed to use later on.
Moving right along to section 2, testing the hypothesis. I like to call this the ultimate battle. So, hypothesis testing proves if observed differences are real or just a complete fluke. Let's say a survey reports that men earn more than women in Austria. Well, hypothesis testing verifies if that gap is statistically significant or just a quirk of who they happen to sample. We frame this as a battle between 2 mutually exclusive outcomes. On one side, in this corner, we have the null hypothesis, or H0. This assumes absolutely no difference between the groups. In our salary example, H0 firmly states that men and women earn exactly the same. On the other side is the alternative hypothesis, H1, which assumes a difference does in fact exist. Your entire goal in an HCI study is to gather enough evidence to confidently reject that null hypothesis.
Let's move to and see how this builds into a very comforting, repeatable pipeline for every single research journey. You start with a subject, formulate a question, state your hypothesis, gather your data, run the test, and finally reach a conclusion. Following this exact sequence is your safeguard. It ensures you don't accidentally jump to conclusions before the math actually backs you up. And now for some dramatic flair. The moment of truth usually comes down to this magic number, 0.05. This is our standard level of significance, also known as alpha. When you run your statistical test, it spits out what's called a p-value. If that p-value is smaller than 0.05, it means there's less than a 5% chance that the difference you observed was just random luck. So, when it falls below this threshold, boom, we proudly reject the null hypothesis and declare our findings statistically significant.
All right, section 3, choosing the right tool. This is essentially the match game. Picking the right statistical test isn't magic. It's honestly just a matching game. Let's look at one of the heavy hitters, the t-test. But hold on, you can't just use it blindly. It has strict assumptions. Your dependent variable must be numeric, the data should be roughly normally distributed, your observations have to be independent, and the 2 groups should have approximately equal variances, which we double-check with a Levene's test. If that last assumption fails, actually, scratch that, don't panic, you just adapt and use Welch's t-test instead, which handles unequal variances beautifully.
Because depending on your data situation, your chosen test changes entirely. Here's your master toolkit. If you're comparing a numeric outcome across two independent groups, like say task completion time, you'd use an independent t-test. But what if you're looking at categorical data? Let's say you're comparing purchase completion, just a simple yes or no, between app design A and app design B. Well, that's two categorical variables, which means you need the chi-squared test. See? It's all about picking the right key for the right lock.
Of course, let's be real, sometimes our data just does not play by the rules. In HCI, we are constantly dealing with small participant pools or ordinal Likert scales, meaning those strict parametric assumptions totally fail. When that happens, non-parametric alternatives like the Wilcoxon, Mann-Whitney-U, Kruskal-Wallis, or Friedman tests step in to save the day. They rely on ranking the data rather than assuming a perfect bell curve. They are incredibly robust alternatives for messy, real-world UX data.
Which brings us to Section 4, avoiding costly mistakes. Let's dig into errors and nuance. Now, what's really interesting about this slide is just because your test spits out a winning p-value doesn't mean you're totally safe from making a massive error. Welcome to the matrix of mistakes. We have type 1 and type 2 errors. A type 1 error is a false positive. That's when you reject the null hypothesis and declare a new design a winner when, in reality, it wasn't any better at all. A type 2 error is a false negative, which is when you totally fail to detect a genuine usability improvement. Honestly, both of these can be incredibly costly for a product team.
So how do we protect against that dreaded false negative? We need statistical power. Power is the probability of correctly detecting a real effect when one actually exists in the wild. This is exactly why planning your sample sizes before you even start testing, doing an a priori analysis, is so critical. In HCI, we conventionally aim for at least 80% power. Without it, you run the very real risk of committing a type 2 error and throwing out a genuinely brilliant UI redesign simply because your sample size was too small to mathematically prove it.
Oh, and here is another major trap, the multiple comparisons problem. Let's say you're testing 5 different UI metrics at the exact same time. Well, doing that artificially inflates your overall false positive rate. The math gets wonky. To fix this, you have to apply strict mathematical corrections to your significance threshold, like the Bonferroni correction or the false discovery rate. We have to be sure we don't accidentally mistake random noise for a breakthrough feature, right?
Finally, Section 5, measuring real impact. We are looking beyond the p-value.
As modern researchers, we really need to shift our focus from just asking, does an effect exist, to asking, okay, but how big is this effect? This is where effect size comes in, because with a massive sample size, even a trivially tiny difference can appear statistically significant. That's why major HCI venues, like the CI conference, increasingly demand that you report effect sizes alongside your p-values. Whether you're using Cohen's d for t-tests, eta squared for ANOVA, or Kramer's v for chi-squared, these metrics tell you the actual magnitude of the difference. They essentially tell you if the improvement is actually worth the engineering time to build.
So, the crucial point is, we shouldn't just rely on binary pass or fail significance tests anymore. Confidence intervals, typically a 95% interval, give us a range of plausible values for the true population parameter. They are highly favored in modern research because they accomplish two amazing things at once. They show you both the estimated size of an effect and the exact precision of that estimate, all packed into one powerful metric. It's the whole shebang.
Which brings us to our final provocative question. What true insights are hiding in your data right now? By understanding your data types, rigorously testing your hypotheses, choosing the exact right tools, and calculating real effect sizes, you're no longer just guessing in the dark. You have a comprehensive, powerful toolkit to take right back to your own UX studies. So get out there, dodge those false positives, and start uncovering the real stories hidden in your data. Thanks for joining me on this explainer, and happy researching!